Reciprocal lattice of a hexagonal space lattice. The primitive translation vectors of a hexagonal space lattice may be taken as a over 2 I hat plus a square root 3 over 2 j hat minus a over 2 I hat plus a square root 3 over 2 j hat and c k hat, where I hat, j hat, and k hat are unit vectors. A. Determine the primitive translation vectors of the reciprocal lattice. B. What type of lattice is the reciprocal lattice? So first of all, I see here the hexagonal space lattice. You can see that we have two hexagons on top of each other, and the vectors A, B, and C are like this, and each side length is A. And the primitive unit cell that would be defined by these vectors is basically the shaded area here, where I have it's being spanned by these primitive translation vectors A, B, and C. So that's the primitive unit cell. Okay, so let's start with direct lattice basis vectors. We have the A vector, that is a over 2 I hat plus a square root 3 over 2 j hat. And you can see why that is the case here. The angle between these lines here will be 60 degrees. So if you have basically the projection of this vector, which has a magnitude a, to the y-axis, you would see that you would need to have a cosine 30, which is a square root 3 over 2. And then you would need to have a cosine 60, which is a sine 30, a over 2, projection onto the x-axis, etc. So this is how I can visualize this. All right. So the B vector is similarly minus a over 2 I hat plus a square root 3 over 2 j hat. So it has the same projection onto the y-axis, but the projection onto the x-axis is opposing that of the a vector. And C vector is c k hat. Now what I would like to do is to find the volume of the primitive unit cell. The volume of the primitive unit cell is given by A dot B cross C. So for that I have to evaluate B cross C, the cross product of these two vectors, B cross C. So I have to find this determinant of I hat, j hat, k hat. The x component is minus a over 2, y component is a square root 3 over 2, z component is 0, and then 0, 0, c. So we have to evaluate this determinant. And for the first row, we have plus, minus, plus. So this is going to give us, for the determinant, a c square root 3 over 2 I hat, and then we will have plus a c over 2 j hat. So if you remember, for example, to evaluate the I hat part, we have to cross these, and we find the product of a squared 3 over 2 with c and subtract from that 0. And if we want to find the j hat component, we have to cross this one and this one. It would be minus ac over 2 minus 0, but because we have the minus sign on top of j hat, it would be plus ac over 2 j hat. So that's how we find the determinant. Okay, now I'm ready to evaluate the volume of the primitive unit cell. The volume of the primitive unit cell will be dot product a over 2 I hat plus a square root 3 over 2 j hat with this cross product ac square root 3 over 2 I hat plus ac over 2 j hat. So this will give us, for the I hat component, a square c square root 3 over 4. I hat is 1, but I hat j hat is 0, so the cross term doesn't give us anything. And for the j hat component, I will have a square root c square root 3 over 4 j hat. So that gives us a square c square root 3 over 2. And by the way, in this cross product here, if you look at the k hat component, you would cross this one and then this one, but then you have two zeros here, so the answer would be 0 for the k hat components. So that's basically why we don't have a k hat component here. Okay, now we have evaluated the volume of the primitive unit cell, and I want to check that what I have labeled here as the primitive unit cell is actually correct. So if you remember, the definition of the primitive unit cell is it contains only one lattice point. So what I would like to do is check. So let's check the number of lattice points in the designated primitive cell. So if I look at one conventional unit cell, this is going to have, from the setup here, as you can see, 3 of these primitive unit cells. So it's going to contain 3 primitive cells. So if I show that there are 3 lattice points in the conventional unit cell, then I would have 1 lattice point in the primitive cell. So what is the number of points in the conventional cell per conventional cell? Okay, so let's count. I have 6 lattice points on top, and they're going to be shared by a top unit cell and a bottom unit cell. So there's a factor of 1/2, and because of the 120-degree angle, for example, here I would have 120-degree angle, so it's going to be shared, because the total is 360 degrees. 1/3 of this one is inside this unit cell, and 1/2 is on top and 1/2 is at the bottom. So I will have 1/6 of this lattice point included in this unit cell. So with that, I will do the same thing for these 6 lattice points here. So I will have 1/3 from the 120 degrees divided by 360, 1/2 from top and bottom unit cells, and there are 6 lattice points. And this is for the top plane, but I have also the bottom plane, so 1/3, 1/2, 6 from the bottom plane, and then I have the center atoms, or the center lattice points. You can see here, they're totally inside the unit cell, but only shared by top and bottom cells, so half of them are in the conventional cell, so center points. So what I would have as a result is 1 plus 1 plus 1, that is 3. So I have 3 lattice points per conventional cell. So what is the number of points per primitive cell? because I have 1/3 of the conventional cell occupied by the primitive cell. 3 divided by 3, 1. So this really checks. So therefore, what I have suggested as a primitive cell is a primitive cell. Okay, so in part A, we want to determine the primitive translation vectors of the reciprocal lattice. So this is the procedure. For the capital A vector, the first vector, we will have 2 pi divided by the volume of the primitive unit cell, B cross C. So we have vector A, vector B, vector C here. So we're looking at B cross C, and then we will look at C cross A and A cross B, the cyclic permutations. Okay, so this will give us 2 pi multiplied by 1 over the volume of the conventional cell. That's 2 over A square C square root 3. Then I have the cross product B cross C. I have evaluated that here. It is AC square root 3 over 2 I hat, AC square root 3 over 2 I hat plus AC over 2 J hat. So that gives me, you can see that the AC square root 3's will cancel for the I hat component. I will be left with only an A, and the 2's will cancel. So I will have 2 pi divided by A I hat. And for the J hat component, I will have AC's cancelling. So I will be left with A square root 3, and the 2's will cancel. So I will have 2 pi divided by A square root 3 J hat. So therefore, I find my capital A vector, first primitive vector in the reciprocal lattice, as 2 pi over A I hat plus 2 pi divided by A square root 3 J hat. So this is the first reciprocal lattice primitive translation vector. Now we will repeat the same procedure for the other two vectors. For vector B, capital B in the reciprocal lattice, I will have 2 pi divided by volume of the cell. So I did B cross C. Next one is C cross A. C cross A. And C cross A I have to evaluate. As for that, I have to look at this determinant. C cross A. I hat, that's positive. J hat, negative. K hat, positive. Evaluating with respect to first row. C vector has 0 x component, 0 y component, C z component, and A vector has A over 2 x component, A square root 3 over 2 y component, and 0 z component. So this will give us, for the I hat component, you can see first I will cross this row and the first column, and this will give me 0 times 0 minus AC square root 3 over 2, and because I have the plus sign here, plus I hat times AC square root 3 over 2. So this first term here will be minus AC square root 3 over 2 I hat. And for the J hat component, I will cross the first row and second column, 0 times 0 minus AC over 2, but because of the minus sign, it's going to turn into a plus. So we will have plus AC over 2 J hat. And then we can find the B vector. It is 2 pi times 1 over the volume of the conventional cell, which was the primitive cell, 2 divided by a square c square root 3. Then I have to take the cross product. I have to take the dot product between, so let's see here, 2 pi over vc, and then I have to multiply it with the cross product. So I will have minus ac square root 3 over 2 I hat plus ac over 2 j hat. So this will give us ac square root 3's will cancel, and because of the minus sign here I have to put a minus 2 pi over a I hat, and then AC's will cancel. I will be left with a square root 3, so plus 2 pi over a square root 3 j hat. So final answer for the second primitive translation vector in the reciprocal lattice is minus 2 pi over a I hat plus 2 pi over a square root 3 j hat. Okay, now we can move on to the third primitive translation vector in the reciprocal lattice. That is our capital C vector. So we did B cross C, C cross A. Next one is A cross B. You can see here from the cyclic permutations. So 2 pi over volume of the primitive cell, A cross B. Now I have to evaluate A cross B. So this will be our determinant again. I hat, j hat, k hat. X component of A vector is A over 2. Y component is A square root 3 over 2. Z component is 0. And for B vector, I have X component minus A over 2. Y component A square root 3 over 2. Z component is 0. So this will give me, for the I hat component, I will get a 0. For the j hat component, I will get a 0. I will get a non-zero answer only for the k hat component here. You can see it's going to be a square square root 3 over 4 minus minus, so it becomes a plus a square square root 3 over 4. So I will be taking this product and subtracting this product from it. Okay, so this will give me 2 times a square square root 3 over 4 in k hat direction. So the C vector will be 2 pi 1 over the volume of the primitive cell, 2 divided by a square c square root 3, and then I have the cross product a square square root 3 over 2 k hat, and this gives us 2 pi divided by c k hat. So our final answer is 2 pi divided by c k hat. Okay, now part B is asking us what type of lattice is the reciprocal lattice. So we're going to investigate the lattice defined by these three primitive translation vectors. So let's compare the direct lattice vectors with the reciprocal lattice vectors. The direct lattice vectors were A is equal to A over 2 I hat plus A square root 3 over 2 J hat. The second primitive vector, translation vector, minus A over 2 I hat plus A square root 3 over 2 J hat. And the third one is C K hat. Now I want to compare these with the reciprocal lattice primitive translation vectors. Capital A vector, it is 2 pi divided by A I hat plus 2 pi divided by A square root 3 J hat. The second one we have found minus 2 pi over A I hat plus 2 pi over A square root 3 J hat, and capital C vector we found 2 pi divided by C K hat. So what I notice here is that they have the same form. So I conclude that since these two sets of primitive translation vectors have the same form, I can say that, so the reciprocal lattice is another hexagonal space lattice. But I want to investigate the relationship between this one and the orientation of the first one. For that, I'm going to take a look at the dot product between the direct lattice vectors and primitive translation vectors. C dot capital C, so it's C K hat dot product with 2 pi over C K hat. You can see that this is magnitude of C vector, magnitude of capital C vector, cosine of the angle between them. So this is going to be C times 2 pi over C. The magnitude of the C vector was ck hat is C, and 2 pi over C is the capital C vector magnitude, cosine theta C, and this must be equal to 2 pi. So I can see that cosine theta C is equal to 1. So this C vector is going to be parallel to the capital C vector. But let's take a look at the other two vectors. However, let's take a look at the angle between A vector and capital A vector. It is A over 2 I hat plus A square root 3 over 2 J hat dot product with 2 pi over A I hat plus 2 pi over A square root 3 J hat. You can see here for the I hat components I have A over 2 times 2 pi over A, and then for the J hat components I have A square root 3 over 2 times 2 pi over A square root 3, and this is going to give me the 2's cancel, A's cancel, A square root 3's cancel, the 2's cancel, pi plus pi, which is 2 pi. And this must be equal to magnitude of A vector, magnitude of capital A vector, cosine of the angle between them. So what is the magnitude of the A vector? It is square root of A square over 4 plus 3A square over 4. Magnitude of capital A vector is square root of 4 pi square over A square plus 4 pi square over 3A square multiplied by cosine of the angle between them. This has to be 2 pi. The magnitude of the A vector is A. The magnitude of the capital A vector is 2 pi A parentheses square root of 1 plus 1 over 3 times cosine theta A. So I find that these a's will cancel again. This will be 2 pi times 2 over square root 3. So square root 4 over 3, which is 2 over square root 3. Cosine theta A, that is equal to 2 pi. So that gives us for cosine theta A square root 3 over 2. So that means the angle theta A is 30 degrees. So there is an angle between the reciprocal lattice vector capital A and direct lattice vector A. And similarly, if I look at the angle between capital B and B vectors by taking the dot product, B dot capital B, it is minus A over 2 I hat plus A square root 3 over 2 J hat dot product with minus 2 pi over A I hat plus 2 pi over A square root 3 J hat. This will give us the minus signs will go away. A over 2 times 2 pi over A and A square root 3 over 2 times 2 pi over A square root 3, which will be magnitude of B, magnitude of capital B, cosine of the angle between them. So this will be equal to square root of A square over 4 plus 3A square over 4, magnitude of B vector, magnitude of capital B vector, 4 pi square over A square plus 4 pi square over 3A square, cosine of the angle between them. This must be equal to 2 pi. You can see here because A's will cancel, 2's will cancel, we'll get a pi. A square root 3's will cancel, 2's will cancel, another pi. So the answer is 2 pi. So this is basically magnitude of B vector is A, magnitude of capital B vector is 2 pi over A square root of 1 plus 1 over 3, cosine theta B is equal to 2 pi. Therefore, cosine theta B must be equal to square root 3 over 2. And again, we see that theta B is 30 degrees. So these two answers, theta A 30, theta B 30 degrees, but theta C is, C vector is parallel to capital C, theta C is 0, cosine 0 is 1, theta C is 0 degrees. So we can conclude that the reciprocal lattice is another hexagonal space lattice rotated by 30 degrees about the C axis.